Hi, in this tutorial I'm going to explain a little bit about the softmax units that were used for multi-class classification with deep neural networks. So in the deep learning book, we see in section 6.2.2.3 there's a little bit of a discussion about why we use softmax units for multi-class classification. So it's anytime we wish to represent a probability distribution over a discrete variable with n possible values, we would use the softmax function. So it's a generalization of the sigmoid function that we've been using the probability distribution over a binary variable, right? Remember the sigmoid function took real numbers as inputs and outputs probabilities between 0 and 1. And so the softmax unit is basically going to be doing the same thing, but for any number of classes, not just 2. So going down, basically we have this equation 6.28, which says, well, we have this unnormalized log probability that is predicted by the last layer of the neural network. And it's going to be these real valued z scores, which are W transpose H plus B, where W and B are weights of the neural network. W is the weight matrix, B is a bias vector. We haven't been using the bias vector in class, so you can actually just ignore that. And you can just do the learning with W, and it's usually about the same. And the H is the last hidden layer of the neural network. And so finally, we get this equation where the softmax function is defined in terms of these z values. Again, so these are these real valued scores that are output of the last layer of the neural network before you put it through the activation function. So the activation function that we use at the last layer of the neural network is going to be the softmax function. And the softmax function here, it's defined in terms of a vector z. So the size of this vector z is going to be equal to the number of classes. So if we're doing digit classification in these standard benchmarks to this, that's the size of z is going to be 10. It's going to be a vector of 10 different real numbers. And so when we say softmax z sub I, what it means is that the softmax function is going to be taking as input a vector z, and it's going to be outputting a vector as well. But here we're only showing you what the ith entry looks like. So every one of the I entries is going to be constructed like this. And here we're just showing you one of them. So what it says is to construct the ith softmax entry, what we need to do is we have to take the exp of the ith element of z, right? So if we're talking about if we're talking about I equals 1, so that's the digit either 1 or 0 in the image classification example. That would mean we take the exponential of that real valued score that's associated with that particular digit, and then we divide by the sum over all the different classes j of the exponential of all of those z values. And so what that does is that gives us a number which is going to be interpretable in terms of as a probability, right? So essentially the exponential function, this is going to always give us a positive number, right? So here in the numerator we have a positive number, and here in the denominator we have a sum of a bunch of numbers which are all positive. Remember, there's going to be one number here for every different class in the classification problem that we're looking at. And so a positive number divided by a positive number is going to be another positive number between it's going to be between 0 and 1, because here it's the sum over all of these zj values, and here we know that the exp of one of those zi values is going to be less than that total sum. So it's going to be a number between 0 and 1. So that's why we're using the softmax function. Essentially, it's going to be able to take a vector of real valued predicted scores, z, that comes from the end of the neural network, right, that was defined using this equation, put it through the softmax function, which is defined like this, and we get a vector of probability scores that we can use to train the neural network. And so, I mean, in fact, the log likelihood is going to look like this. And so the point of this equation here is to show that so here, let's walk through the equation, right? So here we're taking the log of softmax of the I. And so what you can see is by taking the log of this guy, right, the log is, right, so the log of the first term is this CI term, log of the bottom term is this this second term, which is kind of a log of some exp term. And the idea is that the zi here is always going to have a direct contribution to the cost function. So even if the the numbers here are going to saturate. So what it means is sometimes the exponential is very big for one of the numbers and very small for all of the other ones, and so this term is maybe not going to be very useful in terms of learning, but this zi term here is always going to have a direct contribution to the cost function, and it's always going to have a gradient that's going to give us some information about how to update the model parameters. So that's what they're trying to explain in this equation right here. So yeah, this is just to give you a little background and theory on what the softmax function is and why we use it for multi-class classification. Thanks for listening.